State what is meant by a travelling progressive wave. The correct answer to this question is to state that a travelling progressive wave is transferring energy. So a full answer would be a progressive wave is a wave that transfers energy from one point to another or between 2 points. This is just something that you're going to have to learn off by heart. Part B. The diagram shows how the displacement of the water wave at a particular instant in time varies with distance. So note, this is a displacement distance graph. And so there are some things that we'll be able to calculate straight from the graph, like amplitude and wavelength. But period, however, we won't be able to find directly from the graph. The amplitude we can tell from the height of the equilibrium position to the maximum crest, or alternatively you can go from the equilibrium to the maximum displacement, the trough, and the answer is 1, and don't forget the units, millimeter. You will not get credit for this question if you don't include the correct units. The wavelength we can also take from this graph because it's a distance on the x-axis. However, let me tidy it up a little bit. And if we get a little bit closer, you'll be able to see that the distance from the maximum crest displacement to the next displacement here can be read off on the x-axis. Similarly, you can start here and find the same place. Now, if we look at the squares, 2 small squares represent 1 millimeter, so the entire wavelength would be equal to 6 millimeters. Okay, so the answer to that question would be 6 millimeters. To find the frequency, we need to turn to the question itself. In the question, it states the period of oscillation of the sphere is 0.027, so the frequency would be 1 over 0.027, which would give us an answer of 37 Hertz. To find the speed, we now use the wave speed formula. Speed equals frequency times wavelength, which equals 37 times 6, but let's turn this into centimeters, times 10 to the minus, not centimeters, let's convert this into meters, 6 times 10 to the minus 3, and that will give us a value of 0.22 meters per second. In this question, we're given both a displacement time graph and a displacement distance graph. So it should be quite easy to read off all the necessary values. If we look at question 1, we need to look at the wavelength. Wavelength we find from a displacement distance graph. So we need to look at the distance from the equilibrium position to the next equal displacement, which is at 3. So the wavelength would be 3 centimeters. Again, remember the units. To work out the frequency, this time we will need the period. And the period we can read off the first graph by looking at the time taken for a complete cycle. If we start at maximum displacement here and finish at maximum displacement here, you'll find the period is 0.25 milliseconds, if we look at the units, ms. So now we have to find frequency, which is equal to 1 over period. So the answer will be 1 over 0.25 times 10 to the minus 3, which gives us an answer of 4,000 hertz. As you can see, they've tried to make this question a little bit harder by sneakily putting in some units which you would need to convert. The speed of a wave is a very straightforward calculation. Frequency times wavelength. So we have a frequency of 4,000 times a wavelength of 3 centimeters. So you need to change the units. So 3 times 10 to the minus 2 to give it to us in meters. And we end up with, which equals 120 meters per second. So this is the next question, and here you have to describe by reference to the propagation of energy what is meant by a transverse wave. So what's important is that you make specific reference to these words. It's actually not that hard. This is interchangeable with the direction of the wave travelling. So the direction that the wave travels, or the direction of energy propagation, is at 90 degrees to the direction of vibration of the particles through which the wave is travelling. It seems like a very complex way of saying something that's pretty straightforward, but you have to remember this terminology. There are two things going on. The movement of the particles, so if it was a water wave, the water particles are moving up and down. And the wave itself, or the energy propagation, is at 90 degrees to that. And both of these elements have to be in the answer. Another way of doing this is by simply having a diagram. These are the particles. They move up and down. And this is the direction of energy propagation. Okay? The next question is super straightforward. Give one example, other than a wave on a string, of a transverse wave, and anything like light waves, water waves is adequate.